After we've taken a look at what forces are conceptually and how forces work conceptually with Newton's first and second law, we're going to take a look at the forces as quantities, which means we're going to look at actually coming up with numerical values for forces. Right? That means that we're going to be taking a look at the vector properties of forces, the units of forces, and how to do calculations with these quantities. So the first thing that we're going to do is we're going to take a look at a definition of a force, which is an action capable of accelerating an object, which means that anything that is capable of accelerating an object can be considered a force. Most simplistically, we take a look at forces as pushes or pulls on objects. And we are also going to look at the fact that since forces are vectors, that means that any force that you have can be resolved into its x and y components, just like every other vector that's possible, which means that the sum of the forces in the y direction will be equal to the mass times the acceleration in the y direction, and the sum of the forces in the x direction will be equal to the mass times the acceleration in the x direction. We can break the resulting acceleration into an x and the y component, just like we can break the force into an x and a y component, because both force and acceleration are vector quantities. So in the previous lecture, we looked at the fact that we could take a look at the net force, or the sum of all forces in the y direction, and if we had a net force, we would know that that would be the net force times the sine of theta. And over here in the x direction, the net force in the x direction would be the net force times the cosine of theta. So furthermore, we could break this down and we could say, since we know that the sum of all forces in the y direction according to Newton's second law will be equal to the mass times the acceleration in the y direction, that means that we know that the sum of the forces in the y direction will be equal to the mass times the acceleration in the y direction, and the sum of the forces in the x direction will be equal to mass times the acceleration in the x direction. And so these concepts should be pretty familiar, pretty comfortable. The substitution of what the x and the y components are into equations should feel pretty second nature by now. Forces can be written into components. Therefore, anytime you're solving a problem in more than one dimension, forces must be written into components. There is one exception to this, which means that if you're looking at one-dimensional motion, you don't have to break that one-dimensional motion into components. Right? So if everything that you're solving happens along one axis line, alright, you don't have to break it into components. You can just say net force will equal mass times acceleration of the object. And so if you've got one dimension, motion along only one line, you don't have to write components. However, if you have motion that is occurring in more than one dimension, you must set your axes and you must break your forces into x and y components. It is so important that you do this. So very quickly, if we labeled this is F1 and we labeled this as F2, then looking at the sum of all forces, we would be looking at the components for just the F2 force, which is not along one of the axes lines, and that would make the sum of forces in the x direction equal to the x component of F2, so that would be the F2 cosine theta. And I'll write this one first because I've established this is my positive direction, and that means that the F1 is in the negative direction, so it would be minus F1. And in the y direction, the only force acting would be the y component of F2, so that would be F2 sine theta. And taking a look up here where we see that the sum of the forces in the y direction equal mass times acceleration in the y direction, and the sum of the forces in the x direction will equal mass times acceleration in the x direction, I could set this equation equal to max, and I could set this equation equal to may. And if I had values, I could proceed to solve for any of those values. So that's some preview or prelude into setting up problems for forces. But one of the things we want to take a look at is the fact that forces have units, right? The sum of all forces, or the net force, will equal the mass times the acceleration. Well, that means that the unit of forces has to be equal to the units of mass times acceleration, and mass times acceleration would be a kilogram times a meter per second squared. Therefore, the units for the sum of forces, or net force, or any force, has to be kilogram meters per second squared. Now, I could ask you to write that all the time in every single type of problem that you solve, but instead I'm going to have you learn a new unit, which is that every time you have 1 kilogram meter per second squared, or the amount of force required to accelerate 1 kilogram 1 meter per second squared, is equal to 1 Newton. 1 N is 1 Newton. And that's, of course, named after Isaac Newton, who did quantify the first, second, and third law for forces. So this is in honor of him. The unit for a force is now a Newton. So let's take a look. If these are the units for a force, that means that every time we do calculations for a force, our mass must be in kilograms, and our acceleration must be in meters per second squared, which means that anytime you have a mass or an acceleration with non-SI units, mass not in kilograms, acceleration not in meters per second squared, in order for us to calculate force in newtons, we must convert those values. So let's take a look at some simple math. If we have a force of 2 newtons and a mass of 500 grams, could we calculate the acceleration? The answer should be indeed yes, because we have Newton's second law relationship, which says that the acceleration of an object is directly proportional to the net force and inversely proportional to the mass. And since we know the mass and the force, we can calculate the acceleration. However, remember that force has units, and we need to make sure to standardize those units because that's given in newtons, which means that if we're going to be calculating, the mass must be given in kilograms, which means that we have to do a conversion. And 500 grams is equal to 0.500 kilograms. So if we're going to calculate the acceleration, then it would be acceleration equals 2.0 newtons divided by 0.500 kilograms, and that would give us an acceleration of 4 meters per second squared. If we hadn't converted the mass units correctly, then not only would our answer not be given in meters per second squared, but the number would be incredibly different. So always make sure to check the units and ensure that the units are SI system units. So we can take a look at another type of problem for forces, and that would be example 4.2, which is an estimation. And remember that sometimes getting a ballpark number is good enough in physics. So we're going to take a look at force to accelerate a fast car. Alright, so Benny is driving a fast car. He's really happy about it. So the first thing that we're going to do is we're going to estimate a force for a situation in which we have a car of mass 1,000 kilograms, and the acceleration that Benny is using is the acceleration that's 1/2 of gravity. So a lot of the times you're going to see in physics that acceleration is given in terms of g's. It's called g's of acceleration, or g force if we're talking about the force of acceleration, the force that caused the acceleration. So here the acceleration given to this mass is 1/2 g, and we know that g is equal to 9.8 meters per second squared. But we're asked to just estimate which means that rounding to less significant figures is going to be just fine. And so I'm going to round g to 10 meters per second squared, which is, instead of 2 significant figures, it's 1 significant figure. And now an acceleration of 1/2 g would be an acceleration of 1/2 of 10, so that means that our acceleration in this case is 5 meters per second squared. So if I wanted to calculate the force, force equals mass times acceleration is going to equal 1,000 kilograms times 5 meters per second squared. So that's just going to be 5,000 newtons. All right, so that's the net force that Benny must provide if he's going to accelerate his car at 5 meters per second squared. Then we could look at a mass of 1,000 kilograms and an acceleration of 2g. So here our estimation would be g still rounded to 1 significant figure. 2g's would be 20 meters per second squared. 20 times 10,000 is going to be 2,000 newtons. And so the math becomes so easy you can do it in your head and go back and count your zeros if you're anything like me. And then in our third estimation with our good friend Benny, Benny is now very, very small. When Benny shrinks, his head does not necessarily shrink with him. And he is now driving in your toy car. And this time he is taking that toy car with a mass of 200 grams and accelerating it at 1/2 g. Well, 1/2 g is still going to be an acceleration of 5 meters per second squared. But this mass is no longer in SI. So we've got to convert the mass of 200 grams into SI, which means 0.200 kilograms. So force equals mass times acceleration. So it's going to be a mass of 0.200 kilograms times 5 meters per second squared, which is going to be 0.400 newtons. But these are estimations, so that decimal with 2 zeros would be 3 significant figures. I'm going to say 0.4 newtons because that is 1 significant figure. So now that you know Benny can shrink, who knows whether or not your bloodstream is safe any longer, or if there's a Benny creeping around in there. And then we take a look at another type of problem, and this is one of the problems that it might be helpful for us to consider our problem boundaries. Alright, so in this situation, you've got Benny in a full-size car, and Benny is quickly speeding toward you, and you hope that he notices you and decides to spare you. So you know that Benny and the Benny car have a total mass of 1,500 kilograms. Benny in the Benny car is traveling at 100 kilometers per hour, and Benny needs to stop within 55 meters in order to not hit you. So we want to know what force, and we'll say what average force must Benny apply to stop in 55 meters. Alright, and so looking at our problem boundaries, we know that Benny must stop within 55 meters. And we know that it doesn't really matter how he stops, just so long as he stops. So we know that finding out the average acceleration that causes him to have a velocity of 0 at the end of 55 meters is going to give us a sufficient answer. So what we really need to find is we need to find the average acceleration that Benny must cause in order to stop in 55 meters. And in order to do that, we can use kinematics, because this right here is motion. and knowing the average acceleration of this motion is a good enough answer. We wouldn't be able to tell you exactly how he did it, if he stopped all at the last second or if he applied a uniform acceleration. All we know is that as long as his average acceleration for this motion is going to get him stopped in 55 meters, that's good enough. So we're going to use some kinematics to solve this problem. And I bet you are super glad to hear that we're going to be using some kinematics. I know I was. So, if Benny is going to stop in 55 meters and his initial velocity is 100 kilometers per hour, then we need an equation that's going to give us the relationship between acceleration, which we need in order to determine the average force. We're going to need our initial velocity, since that's a given value. We know our final velocity because we want Benny to be stopped there, and we know our position. So seeing as these are our givens, it seems we don't really care about time. So I would like to use the equation v squared equals v naught squared plus 2a x minus x naught, because this equation will allow us to solve for the average acceleration, and it will allow us to use the given variables, or the variables that we know we have. So we know that Benny needs to be stopped at the end. We know that our velocity must be in SI units, so I'm going to convert 100 kilometers per hour into meters per second. And in order to do that, I'm going to say 100 kilometers is going to be times 1,000 meters. And that's going to happen in 3,600 seconds. So we've got a actual initial velocity of 27.78 meters per second squared. We could round that to 28 meters per second square, or meters per second, not the squared. See, sometimes I do it too. So I'm going to be solving 771.6 meters squared per second squared plus 2a, and then x minus x naught. If I assume that x naught equals 0, then x equals 55 meters, then that's just going to be 55 meters. Now I can solve for our acceleration. It's going to be negative 771.6 all over 2 times 55 will equal acceleration. So that's a negative value, and I'm dividing by 2 times 55, and I get an acceleration of negative 7.01 meters per second squared. Two significant figures is fine, so I could have said 7.0. And now I have the average acceleration that Benny must have in order to stop. So we need to answer the question, what average force must Benny apply to stop in 55 meters? Well, we know that whatever average force has to happen, right, the result of that force better cause that acceleration, right? If we're going to get the force that has to be applied to give you a stop, then we need the mass of the car, so that means that the force that needs to be applied is 1,500 kilograms times a negative 7.0 meters per second squared, and that would give the car a required force of 1,500 kilograms times 7.0, and that's a negative. That force would have to be negative 10500 newtons. That is the force that must be produced in order to stop the car. If I'm going to round to two significant figures like I did up here with 28, then that force would actually be negative 11 newtons. So here's a quick side comment that I want to make about solving a problem like this. we solved for the net force. I know that we solved for the net force because the net force is what actually caused that acceleration that would stop Benny from ending your life. That means that solving for a problem like this, imagine that Benny and all of the forces that Benny is experiencing and the vehicle are experiencing, imagine it is a black box that you can't see into. All you know is that the net force was negative 11,000 newtons. That's all you know. You don't know whether there were forces pushing forward and forces pulling out. You don't know much about what caused it. You only know that the net force that caused it was negative 1100 newtons. That negative sign means that it was a force in an opposite direction to the motion. Alright, so that means that Benny had to apply a force that changed his motion in the opposite direction. And that was a stopping force. So we do know that it was probably a resistive force. We know that this motion was in one dimension, so we could say for sure that there wasn't a force in the y direction that resulted in this net force. But we do not know if the net force was a result of just the force that Benny applied, if it was the force of Benny and friction, and we don't know if there were any forces pushing the car forward. We don't know that. We can't answer it because it's like a black box in that respect. We can answer some logical questions like the force was along the axis of motion. We can answer some practical questions like the force was a resistive force because it caused it to move and then it caused it to slow down or move, change velocity in the opposite direction of motion. But we can't tell you if the force was completely caused by Benny or if it was caused by Benny and friction, and we can't say whether or not Benny had his foot on the gas and the brake at the same time. We don't know any of that. All we know using this method was the net force that causes that acceleration. And so that's good enough in situations where you're just interested in the average acceleration of an object or the net force that would be required to cause an acceleration. If we start asking questions about the individual forces that an object experiences, then we're going to need to be a little bit more detailed in what type of questions we ask and what type of forces are acting in what direction on the objects that we're asking them about. All right, we know that the net force was a negative force along the axis. That's what we know. But we don't know any information about the actual forces that were happening as Benny was driving. What if Benny did have a foot on the gas pedal? Then we would know that he applied a positive force, a force in the same direction as his motion. But he also had to have put a foot on the brake because we know that the net force was in that direction. But we don't know because we don't know about the size of the force in the forward direction and the size of the force that he put on the brake, and we don't know if maybe there was also some friction involved. We don't know anything about the individual sizes of these forces. All we know is that the balance, the net of what happened, gave us that acceleration. And so that's going to be something that we're going to take a look at, is how do you figure these things out on the inside? And how do you take it from the overall acceleration, the overall motion that was caused as a result of the force, into each individual pieces of force that caused that motion. And that's going to be something really important that we're going to be investigating as we move forward in this unit.